Without delaying any time, I would invite today's first speaker and resource person, Dr. Mudassar Iqbal. Dr. Mudassar Iqbal, the floor is yours now.
Thank you very much, Perez. First of all, I would like to confirm that my voice is clear. Yes, please confirm my voice is clear.
Yes, your voice is clear, but little louder.
Let me share my screen now. Is it in presentation mode? Please arrest confirm me.
Yes, it is clear for me.
Myself, Dr. Mudassar Iqbal, working as a lecturer of CEWRE, Lahore. Today, the part that I'm going to put guys is about the workshop on river modeling.
Dr. Mudassar, I cannot hear your voice. Your mic is very far away from your mouth. And
Now it's clear, sir?
can you put it close to your mouth?
Yes, it is. I think now closed. Okay. So, Wes, can you confirm me?
Yeah, now it's better. Please speak loudly.
Okay. But firstly, Wes, confirm me that your voice is too loudly, so speak a little.
And I will request the participant to raise your question or raise your hand if you have any problem of listening to. I think they have put your mics muted, but you can put your comments in the chat box. So if you have problem in listening, please let us know.
All right. So this part is under the today workshop on river modeling using HEC-RAS 1D 2D features. HEC-RAS, HEC stands for Hydrology Conjunction Center, that is part of US Army Corps of Engineers, and RAS is river analysis system. So the first here is represent kept some outlines of today's this part presentation, this part about theories and about theory of HEC-RAS and its capabilities. That covers introduction of river modeling or hydraulic modeling. The second one we have to do conceptual understanding, then governing impressions, then also why to be we need and how to be is based in HEC-RAS about flow area mesh. The first is as we know that uh, we experience two types of flows in channels. The first is steady flow and second is unsteady flow. The flow, what is steady flow? The flow velocity at a certain section does not change with time. So we say that is steady flow, and where the velocity change at certain point with respect to time, that is unsteady flow. So the examples for steady flow is can be a power canal where we provide a design discharge for the power project, in unsteady case example, like during floods in rivers, the flow velocity changes during rising and falling stages of the flow in the main river channel, or also the floodplains. That is example of unsteady flow. So, but in the river modeling, in river is a natural channel. The flow behavior is highly complicated phenomena due to unsteady and non-uniform flow in rivers, especially if we talk about the river. So, we need to study the characteristics of unsteady, steady, steady flow. Then next, let me move why we need this hydraulic modeling. HEC-RAS goes with HEC-HMS or any hydrological model that provide us peak discharge. So when this peak discharge goes to the river channel, so how wide this discharge goes, how deep this discharge goes, and how fast it moves. So in case of flood mapping, the flood plains we consider flow is much wider. Flow is much wider than river main channel. So just in the hydraulic modeling, our idea is to just estimate the flow velocity, flow depth, and the width when peak discharge flow through it in river. So this is the main concept that uh, we follow in the river. Now, the some conceptual understanding about 1D or 2D. So let's suppose we have a river plan. The river is river moving downward, the river flowing downward from and the water comes from the ground from this side. Can you confirm me, Wes, my cursor when I move my cursor, it, it is also displaying at your screen?
Yes, Dr. Sab, it is clear on your
Or,
screen.
or if I if I shift to the cross section of this plan, so we can see that what 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 comes from the this ground, or we say plains, uh, and also water comes from subsurface. Then uh, then water rise from downside to upside till it goes to the floodplains. So similarly, similarly, uh, water water comes to the water comes to the channel. Water is out. Water is going out to the floodplains. So this uh, we can see that we are seeing that flow is just wait a second.
Your voice is muted, sir. I think your voice is not clear. I think there is a problem in your microphone. No. Okay.
So yeah, now my is clear. Rest, can you confirm? Just wait a moment. Now I will be confirming my voice. Either it's clear at all the spots. Yes, it is clear now.
Yeah, it is
Oh,
much better.
oh. So on screen also. Yeah.
Yes, it is visible, sir.
Okay. So when we have water coming and outgoing flow from the different directions, then we can say that at the time we have uh, river flow in the along the channel and to the sides the channel, and at the same time water is also rising at the in the main channel, and it goes to also the floodplains. Then we can say that we we have flow in our three directions. Like we can say in the main channel along the channel it is x, to the floodplains it is y direction, and towards the upward in the main channel or the floodplains towards upside it is z direction. So we have here we can say that it is three-dimensional flow. Normally, what happens, most of the cases, we consider that uh, the impact of the flow that is moving in the main river channel along the channel is much stronger than towards the floodplains or to the upward. And in that case, we can ignore these two directions, and then we usually say that it is one D flow. So, so what will happen? It means that if we neglect, it means that we are if we neglect the flow towards towards floodplain or towards upside in the channel, then it means that we are not considering hydraulic changes that occur in other directions, and we take uh, only in one direction, that is x. So in this case, we will say it is 1D. If we consider in the floodplains directions too, that will be the two-dimensional flow. So next is the governing equation. A governing equation that follows the HEC-RAS is one descent Bennett equation that that use implicit finite difference method for the for is a numerical method for solving it. So it is based on continuity equation and momentum equation. Continuity equation is basically the conservation of mass, and momentum equation conservation of momentum. So in continuity equation, we can see that the first part is change of area with respect to time, and the second part, which is changing in flow with respect to the distance. But here we see that C and F, this is the main second part, which is the change in flow with respect to distance, and C and F, which we are seeing in both equations, that these terms refers to the floodplain flow area in floodplains, or C is for channel flow and flow area or velocity in channel. So in the momentum equation, it is a little bit complicated, but we simplify it in this form dz over dx plus x. Like, for example, if we consider the discharge flow with respect to time, if we, this equation has four components. First is local acceleration, second is convective acceleration, and the third and fourth is about pressure and energy terms. If we say that this discharge is not changing with respect to time, then or we assume that it is steady state. So then we can consider or we can neglect it. The second part uh, also is about the change of flow, uh, change of flow with respect to distance, and C and F same for flood and channel, for terms for flood and channel terms. And this this happens, convective extension happens when the flow is in the river, concerns with the structures and convection, expansion and contraction happens, then this convective accelerations component active. Uh, but most of the cases we also neglect this part. The remaining part is pressure and energy, and we can see here it is a potential factor, or we can say it's elevation. So we simplify it curly z, like it's a derivative of z with respect to x. So we simplify it dz over dx plus slope is equal to 0. So this is a simplified form. That we try to solve this equation, which is simplified form. By how we will solve this, by adding the energy equation here. So next is 1D profile calculation in HEC-RAS. Here we again suppose that actually here again we have a plan of river, and the river water is flowing upstream to downstream. This is a longitudinal profile of like here is z, y, and v is the velocity head, v square over 2g is a velocity head, y square is a depth, and z is a elevation potential. And similarly at the downstream at section 1, these are the same variables. And here we have HE, that is energy loss or heavy loss. This is a basic equation. We have familiar with this equation, which are Bernoulli from the Bernoulli equation. Here I am calling it as an energy equation. So here A2 or A1 are the velocity weighing coefficient that we, let me explain the next slide. And the HE we calculate from this expression. Later in this expression, the L is a reach length. So first is, this slide is part of the previous one. So here we have again plan view of the river, and we have two cross section. Flow is moved upstream side to downstream side, and this we need to solve this equation. And in this equation we have L reach length, and the reach length here we determine with this equation. That is a representative length from by taking into account from three lengths. One is leftover bank length, that means the section from the left side, and the right over bank, ROB denotes the right over bank length between the cross section, and LC is a channel length. So L is a representative length that we determine from this expression. Similarly, QLOB, Q channel, QROB represents the left, right, and channel parameters. Now, uh, here we know that here in this equation we know at cross section we have also varying velocity at floodplains, LOB at LOB side, at ROB side, right side, and the main channel side. So the velocity heads also will be different. So to adjust these velocity, we use A2 or A1 is a weighing coefficient. Means we find the average cross-sectional velocity head. So this is also the part of the previous 1D profile calculation. So here in the last slide we calculate the L, and here we are trying to calculate the SF, that is the left part of the head loss. From this equation, we we determine the this SF, and we relate this equation with Manning's formula, and we determine the conveyance K from this equation, and we put and SF we determine from this equation, just replacing the factors from one side to another side. And the mean SF from one section to another section, we need to divide the discharge with this conveyance, and the discharge with its conveyance, the second. So in computational flow here we find uh, conveyance K and SF are based on the Manning's value. So we need to carefully select these values. So if I sum up the previous 2 or 3 slides, so we have energy equations here, and we need to determine here, mainly we need to determine here the flow velocity and depth. But for it we have to also calculate the HE. So usually we start it with the boundary conditions. This step is very important. Please uh, just just make a little bit more consideration here. So here, what we do, so we start the modeling with the boundary conditions. For example, in steady state condition, we assume known depth as a downstream boundary condition. Then, and upstream boundary condition is Q. So what we do here, so now if we have considered it is a known, and with known y1, and we have assumed we need to assume y2. So we with assumed y2 and with known y1, we calculate or we find the HE. Not directly, with the help with the findings of K and friction slope and conveyance. Then we get y2 by putting the head loss value in this equation. If our computed y2 or assumed y2 is greater or equal or within the range of tolerable values, then we suppose that our assumed condition is good. And then we will move upside. If our assumed y2 and calculated y2 are not in the tolerable range, then we repeat or we assume y2 again. So in case of the acceptable, so we move upward side and the y3 side, and the y2 will be the y1 and y3 will be the y2, and we will and the HEC-RAS or we will do the same things at the second cross section or second breach length. Then we say it is a standard step method. So now, now is a hydraulic capabilities of HEC-RAS. HEC-RAS currently HEC-RAS has the following four type of capabilities to do or to perform the for simulation. First is 1D steady flow water surface profile. And here in the last slide, I discussed about this water surface profile. And the next, the capability of the HEC-RAS is 1D or 2D unsteady flow simulations, which HEC-RAS works for unsteady flows also. Now, sediment transport computation is also we can be modeled the HEC-RAS. And the last one is the water quality analysis we can perform in the HEC-RAS. But here, in this webinar or training portion, we are focusing the first two points, that is steady flow water surface profile or 1D or 2D steady flow simulation. So why 2D flow computation required? Why we go to the 2D? That basically when we see a non-prismatic channel with varying cross section or bottom slope is a basic definition of the non-prismatic channel. So in non-prismatic channel with varying cross section and bottom slope, we see that we have different value at the same cross section. We have different flow depth, velocity at same cross section. And the second is lateral flow from breach type, where when type breach, then the flow velocity is higher. At that place, flow velocities are more higher. If we do here 1D modeling, then the velocity will be less. Then we will get the less velocity value. But actually, there is a higher velocity value. And flow around the spur, if we have a tide along the river, along the flow, then there also water is stagnant and the depth is more and velocity is less. So in this picture, the right side one, you can see that this picture shows the velocity magnitude or velocity profile. So here, due to the obstruction across the river, so here velocity is very less because the water is stagnant at this part, and the less velocities we can see here. So the coordinate equations for 2D flow is the Sandbennett equation, that is full momentum equation form we use to simulate the 2D flow, and its form the Fian wave, the HEC-RAS we use this form allows the software to run faster or stability is higher as compared to the others one. So for solving these equations, we have some numerical methods, implicit or finite volume advantages for these methods, implicit or explicit tag. that is approximations, because it's the in these equations, 2D equations, as a non-linear, that we have two independent variables. So we cannot solve it, and numerically we need to solve it. For that, it is approximation. We approximate by these methods. So then in the 2D part, what we do, in HEC-RAS offers two types of 2D flow area mesh. One is structured and another is unstructured. in computational cells can be triangles. Unstructured means not in proper shape. Mesh or rectangles or grid. Grid is not in proper shape. Can be triangle, square, but up to 8 sides we can put HEC-RAS 8 sides grid. Structured mesh orthogonal cells simplifies numerical discretization and increase efficiency of computation. So this is actually the 2D. Uh, in 1D, we work on the cross section, but in 2D we work on the mesh, and we design our mesh according to the we fix our size the mesh according to our terrain uh, that we have actually. Like for example, CRAS 2D uses the subgrid bathymetry approach. In this approach, bottom is not considered bad with a single elevation. So, for example, if we have 200 by 200 grid on a terrain, of the terrain resolution is something else, and the CRAS 2D is 2D model resolution is something else. So, it can work 2D flow area preprocessor will compute elevation volume relationship based on 5-meter resolution. So it means that our grid is our gridding, our fixation of grid is not matter. The main thing is the terrain resolution or DEM we are using. So cell face is evaluated according to the cross section for exact wetted area and other parameters. So here the point is that whatever the area in the cell is wet, that will be there. Whatever the amount of area is wetted, there will be also computation by HEC-RAS to be used. So where the flow can be retained while doing 2D, while doing 2D, that is flow controlling, that is road, high ground, and weir. And in this picture, we can see that these are the high grounds, the road, and this along the not along across the river, the weir. So here, controlling these are flow controlling terrain features. These features can only control the water retention in this feature of the grass that is 2D. Here, up to here, whatever we discuss is about that what is going on behind the HEC-RAS. So the reference is addressed from where that I present the literature is from reference manual or open channel flow book by Muhammad Hamid. It's the second version. So now what we do for in HEC-RAS, that is actually do in HEC-RAS, that is another part that is flow formulation of model, HEC-RAS model, and simulation and hands-on exercise. So I think now I